Okay, good evening everyone. So just a quick recap. So in the previous lecture, we basically discussed the reason behind having a fixed size for splitting the bytes which we have, splitting the bits which we have. Imagine we have a very long string of bits. Now how do we know its source, right? Whether one particular number is converted into this string of bits, or 2 3 characters are converted into the string of bits, or some 100 characters are converted into the string of bits. We don't know that, right? So we cannot decode this uniquely. When you try to decode this, you may get multiple mappings depending on how you are splitting it, right? For instance, if you are splitting two bits, then 10 bits, then 5 bits, you are grouping them arbitrarily and then converting them, decoding them, you will get different results. So a standard is fixed that 8 bits. Yeah, can we have some silence, please? 8 bits is one chunk. Okay, that's called a byte. We all know that. So 8 bits is fixed because 8 bits is sufficient size to represent 256 different characters. So if we have 8 bits, that is good enough size to store 256 different characters, and it is fixed. So you read 8 bits at a time, 8 bits, then 8 bits, then 8 bits, and so on. So 1 byte is the minimum unit in computing, in programming or computing or whatever. Okay. So these are all some examples which we discussed yesterday, and then we discussed data types. We first looked at char. Char is basically an integer data type only. Okay, because it stores numbers only at the end. It stores numbers from 0 to how many bits char has? Bits, yeah. 8 bits. 8 bits means how many different possible values? 256, because 2 power 8. 2 power 8 different possible values, that is 256 different possible values, but the range of values is 0 to 255. If it had started with 1, it would have gone to 256, but since it started with 0, it goes only up to 255. Okay, but the total number is 256. Fine. So a char is basically an integer which can store numbers from 0 to 255. Now, why are we calling it char? Why are we not calling it int or something else? It is because this particular data type, which is whose size is 1 byte, it is mostly used not for numerical computation but for character storage or character comparison, etc. Because this particular data type is used mostly to deal with characters, it is called char. But fundamentally, this is integer data type only. So whatever you can do with integers, you can do with this also. Okay, but the only thing is here the numbers range between 0 to 255. So if you know your numbers range only between 0 to 255, you can use this particular data type. If you know that your numbers go beyond 255, then this will not be sufficient. So you have to use a larger data type. Okay. Now a char data type, since like I said, since it is also integer, you can perform integer operations on that. For instance, I can subtract character A from character C. C minus A. What will be the answer? Huh? Whatever is the number of A, whatever is the number of C, C minus A will be, it's not whatever is the number of C, depending on the number of A, C's number will be decided, ASCII value, right? So then C minus A will be, suppose if A is 1, B is 2, C is 3, D is 4, and so on, then C minus A will be 2. Suppose A is 97, then B is 98, C is 99, D is 100 and so on. Then C minus A will be 2. Suppose A is 10, B is 11, C is 12, then D is 13 and so on. Then C minus A will be 2 only. You don't need to know the ASCII values to find out C minus A. Right? C is just 2 letters away from A. So C minus A will be 2 only. Okay? So you can actually do C minus A as well. You can also do C times A. You can multiply. Basically, it will convert them into corresponding ASCII values and perform the integer operations on them. Okay? But fundamentally, this is an integer data type. Just keep that in mind. The name is only char, but it is one of the integer data types. So if someone asks you what is the integer data type with size 1 byte, it is not short int or short int or some int. It is char. The name is char. So char is an integer data type of 1 byte. If that is not sufficient, we need to go to the next data type. What is that? Short int. Short int size is 2 bytes because 8 bits are not sufficient to store numbers larger than 255. You need to increase. Now, when you increase, since we sort of just now discussed that the basic chunk, the smallest chunk of bits you can think of is a byte. So you can't increase by 1 bit, you have to increase by 1 byte. Okay? So char is 1 byte, short int is 2 bytes. Now, these 2 bytes are treated as one chunk. So 16 bits are treated as one chunk. So now whatever numbers can be stored using 16 bits, how many different values can be stored using 16 bits? 2 power 16, right? And the minimum value is 0. Maximum value is 2 power 16 minus 1, right? So now, earlier you were able to store only 2 power 8 minus 1, largest value. Now you can store up to 2 power 16 minus 1. Why? All the 16 bits are grouped. So you convert all the 16 bits together into a polynomial version to get the decimal number. Earlier you had 8 bits and then 8 bits, so you couldn't group them and convert to get a larger number. Now you can group them. Now you can consider all the 16 bits to be of the same number and convert those bits into the polynomial version to get the decimal number, right? How do we convert binary to decimal? You take the binary digits, give place values to them, like the rightmost one is 2 power 0, then left one is 2 power 1, then 2 square, 2 cube, and so on. Whatever is the leftmost one is 2 power n. So you take the digits and multiply them with their respective powers of 2 and add these values. So this will give you a polynomial expression. And when you evaluate this polynomial expression, you will get a decimal value, right? So the more bits you have, the larger number you get, the larger decimal number you can store. So earlier you had only 8 bits, you can store only up to 2 power 8 minus 1. Now you have 16 bits, you can store up to 2 power 16 minus 1. So all these 16 bits will be converted to polynomial. You will get a decimal number, so that will be the largest value. Then, even if that is not sufficient, 2 power 16 minus 1 is also not a very big number. It is like 65,536. That's all. But we deal with lakhs, millions, billions, right? So we need larger numbers. For that, the next size we take is 4 bytes. So all the sizes are in powers of 2. Okay? The number of bits in a byte is in powers of 2, that is 8 bits. The number of bytes we take is also usually in powers of 2. 1 byte, 2 bytes, 4 bytes, 8 bytes, etc. We don't take 1 bytes, 2 bytes, 3 bytes, etc. It is always in powers of 2. Okay? So the next, after short int, the next data type is int. Okay? Now short int, long int, etc. When you write in C, you can write as short int or you can just write as short. It will understand it as short int. Any way you can write. Int is only int. Int size is 4 bytes. 4 bytes means how many bits? 32 bits. 32 bits means how many different values can 2 power 32. So the smallest value is 0. Largest value is 2 power 32 minus 1. Good. So now much larger number can be stored in int data type. So depending on your problem at hand, you should choose a particular data type. For instance, if I am dealing with the ages of people, students in this class, you almost belong to the same age, but I say ages of all the people in the institute, they may range from whatever number to whatever number. So which data type suits the best to handle this problem? Char. Although these are numbers, char is sufficient to deal with them because the range is, it's not more than 255, right? In fact, it won't even be more than 100, 120 at max. So 255 is more than enough. All right. So char is sufficient. So whatever you want to do with these ages, add, subtract, compare, whatever it is, you can just use char data type. Because if you use short int, you are unnecessarily wasting space. When you can do with 8 bits, why are you using 16 bits? Okay. So char is a more suited data type. If you have some other purpose, maybe if you are calculating the distances between planets or something, then even integer may not be sufficient. Then you may need to use long int, or even that may not be sufficient. You may need to use long int, right? And sometimes distances may not be just integer values; they can be real numbers, right? Then integer data types are not sufficient. You need to use other data types like float, double, etc. We'll see them. Look at them later. Okay. So this is one thing we discussed. And I just mentioned variable declaration syntax in C. So in C, you have to mention which, what is the value you're dealing with, right? And this value is stored in some variable. So why do you need a variable? Why can't I just use values? I can directly give values also. I can use C or Python or any of them like calculators. Huh? No, why? Direct number is faster, no? I store that number in a variable, and then variable I need to use. So whenever it sees a variable, it needs to decode what number is stored in that and then use that number. Why two, 3 steps? I can directly give number. Yeah, I can directly use those different types of values. Why do I need to store them in a variable?
We need not remember the numbers.
Right. That's all. See, there are various uses of variable. One, to minimize errors. Like when you're writing a code, suppose I want to calculate, I want to implement a function. It's a complex function. It's like 2x power 5 plus 4 dx by dy plus 7x cube, something, some complex function I have. It is all made up of x. Okay. Now, say take simple function x square plus x plus 1. Now this thing, I know the first one is x, the second one is x. Now suppose I also know x is say 25. One way of writing is I can write 25 square plus 25 plus 1. Now suppose the expression is slightly longer. There is a possibility of making some mistake somewhere. Rather than writing 25, you may write just 2, or you may write just 24 or 52, right? So 25 square plus 25 plus 1 minus 52, you may make mistakes somewhere. So if you try to write that every time, instead of x, these numbers are all same, right? It is x square plus x plus 1 or x cube plus x square plus x plus 1, whatever it is all x. So just store 25 in x in one line. Write just one line to store 25 in x. Done. Now you use x any number of times you want, right? Otherwise, if you have to reuse that number every time, you may make mistakes. You may write 24 instead of 25 or just 2 instead of 25, whatever it is. You may make mistakes, right? That is one thing. Second thing, sometimes I don't know the value beforehand. Okay, I just want to keep some space for that. Or I may take the value from the user. Okay, I want to take the value from the user and then do something with that. Now, at least for that, I need a variable, I need a container. So I say, okay, this is the container, you put your value in this. And I can have 3-4 containers. So I need 3-4 different variables. So these 3-4 different variables will have different meanings. For instance, I can say just I'm storing students' data. I can have a variable like age, roll number, year, semester. All these are variables. Now, if I sort of distribute this program to all of you, and you're all supposed to enter these values, right? It's like a Google form. Imagine I have a Google form. I sent the link to all of you. Are supposed to fill that Google form. Now, how does the Google form store this? It stores these against some columns: your name and your age, roll number, which year you are in, which semester you are in. These are all values, so that I can select all the values based on the name, like sort students based on their roll number. So roll number is a variable in which different values can be stored. All right, you can add variables, multiply them, you can perform all kinds of operations on variables. You can store them, you can reuse them, you can also use them in a function, you can update their values, right? You can perform an operation on multiple variables and store it in a different variable. So basically we need containers. Variables are containers which store values. Okay, you will get a better understanding when you write some programs. Fine, so we have a variable. Now that variable, a computer needs to understand how to decode this variable. Every variable is in terms of bits only, right? It's in binary. Now, how does a computer know how to decode these bits? We know it can decode 1 byte at a time. But even if it is 1 byte at a time, it may not know how to decode it unless we tell it what kind of the data is present in that 1 byte. You will see, we will just see an example. Suppose we are using shortend or we are using int. Now it is not 1 byte at a time, it is 4 bytes at a time. So a computer should understand, now beginning from this point, I should not stop at 1 byte. I should go all the way up to 4 bytes and then take this entire bit number together, bit string together and convert it. How does the computer know that? You need to tell it. So we should tell it, don't take 1 byte, take 4 bytes. Or don't take 1 byte, take 2 bytes. Or don't take 4 bytes, take 8 bytes. So how to group? Minimum grouping unit is byte, but again bytes you may group at a higher level. You may group 1 byte, 2 bytes, 4 bytes, 8 bytes. How does the computer know how to group these bytes? You need to tell it. How do you say that? Using data types. You say, okay, this is an integer data type. So the computer knows, okay, now I shouldn't group 1 byte, 1 byte, 1 byte, etc. I should group 4 bytes, 4 bytes, 4 bytes. So it takes all 4 bytes, converts it to a number, which means it takes 32 bits, converts it to a number. This it is doing because you are telling it this is of integer data type. So my number is so large that I need 4 bytes to store it. So you treat it as an integer. You take 4 bytes. Otherwise, I know my number is very small. Char is sufficient. 1 byte is sufficient. So I call it char. Now, since you said this variable is of type char, it will just look for 1 byte size and convert that 1 byte into a number. Okay. So you need to explicitly mention what type of data you are dealing with to the computer. That is why you need both the things, the data type and the variable name. And value you can assign either in the same statement or later. So 3 things are there: data type, variable name, value. When you are declaring a variable, minimum data type and variable name should be given. Value is optional. Okay. Okay. Now we also looked at this question. What about negative integers? Earlier, so far, whatever we have seen, we dealt with only positive integers, right? If it is 8 bits, 2 power 8 different values, 0 to 255, that's fine. But what about negative integers? We also saw that putting a hyphen, giving a value to putting the character and then an integer next to it does not make it a negative number. It is only a visual representation. See, hyphen is not a God-given thing that negative number should be represented only with hyphen and then the number, right? It is a convention. That's all. Instead of hyphen, you could have used exclamation mark or tilde or hash or whatever to represent negative numbers, and that would have become the convention. So there is nothing inherent in hyphen which tells us that this is a negative number. So even when you want to perform operations on numbers as a negative number, when you multiply 2 negative numbers, you automatically get a positive number. Or when you subtract a larger negative number from a positive number, you end up with a negative number. All these things, these are inherent properties of negative numbers. So you should try to capture that inherent property within the number itself rather than using some additional symbol which in no way captures this inherent property. It is only associated with that. It is not giving meaning to that negative number. Okay. So the point is, we know numbers have only two signs, positive or negative. So since there are only two values, they can be represented using one bit, 0 or 1. So rather than using the entire 8 bits or 16 bits or 32 bits for the magnitude of the number, we will use one bit, the first bit, as the sign bit to say whether it is a positive number or a negative number, and the remaining n minus 1 bits for the magnitude of the number. What is the size? What is the, what is the magnitude of the number? So now the magnitude reduces by how much? It reduces by one bit, but in terms of decimal values, it reduces by how much? Suppose 8 bits earlier, it was 256 values. Now you reserve one bit for sign bit. Now you got 7 values, 7 bits, sorry, 7 bits. So now how many possible values you can represent magnitude wise? 2 power 7. So it reduced by how much? Huh? So what is 2 power 8 minus 2 power 7? That is 2 power 7 only. 128. Suppose if I had 16 bits, it was 2 power 16. Now it will be 2 power 15. One bit is gone for sign bit. I have only 15 bits. So it became 2 power 15. Now it reduced by how much? 2 power 15. Can you generalize this formula? N bits. Simpler way. The magnitude will just reduce by half. You had 256 values earlier, now you will have 128 values. You had 512 values earlier, now you will have 256 values. That's all. It will reduce by half. Now, it is not technically reducing. The positive range is reducing by half, and it is compensated by equivalent amount of negative range. So you can just imagine you have a real number line. I have numbers from 0 to 100. I just shift them 50 places to the left. Now I'll have numbers from minus 50 to plus 50. That's all. So 50 positive numbers reduced. In place of them, 50 negative numbers got added. That's it. So that is what is happening. So still the total number of different values which you can represent is 2 power 8. Only the range has shifted, but to the left by half. Earlier it was 0 to 255. Now it is minus 127 to plus 127. That's all. Okay? Fine. So suppose if you take plus 6, it is represented as 110. Now all the remaining you fill with zeros. Now if you want to represent minus 6, first you represent it as 110, fill all the remaining with zeros except the first bit. First bit will be 1 to indicate it is minus. Alright, so this is the sign bit. Now within this bit representation, so this is called the most significant bit, and this is called the least significant bit. So this position, when you are representing a number in bit representation, the rightmost bit, the units bit, is called least significant bit, and the leftmost bit, whatever is power of n. Silence, please. So whatever is the power of n, it can be, suppose I have 4 bits, 2 power 0, 2 power 1, 2 square, 2 cube. So here 2 cube is the most significant bit. If I have 5 bits or 6 bits, then 2 power 4, 2 power 5. 2 power 5 is the most significant bit. That's it. Rightmost one is the least significant. Units place, tens place, hundreds place and so on, like that. Similarly in binary, units place, twos place, fours place, eights place and so on. So the leftmost one is the most significant bit. Okay, so in signed representation, the most significant bit is a signed bit. Okay, so now a new thing got added. Now in the data types, each of the integer data types, now you have two categories, unsigned and signed. So in char, you have unsigned char, signed char. In shortened, you have unsigned shortened, signed shortened. In int, you have unsigned signed. In long-int, unsigned signed. In each of integer data types, you have both varieties, unsigned and signed. Now, it is by now clear. So if you take an integer, if I know, or let's take shortened, if I know the range of numbers, I am dealing only with positive numbers, and my numbers range from say 0 to 50,000. Okay, then I use unsigned shortened. Okay, because when you say unsigned, you know there is no positive negative sign there, there is only positive. And since you know it is positive, you don't waste one bit for sign bit, you will include that also in the magnitude. So now all the 8 bits or 16 bits or 32 bits will be included in the magnitude. This is like the original thing which you learn. 8 bits means 2 power 8. 16 bit means 2 power 8 bit means 0 to 2 power 8 minus 1. 16 bit means 0 to 2 power 16 minus 1. Like that. You have only positive numbers. So if you know you are dealing with only positive numbers, you can use unsigned data types. If you know you are dealing with both positive and negative, then you can use signed data types. Okay. For signed data types, you don't need to write explicitly signed. If you don't mention anything, signed, unsigned, etc., it will assume you are using a signed data type. So if I just write shortened, it will understand it as signed shortened. If I just write int, it will understand it as signed int. But if I want to use unsigned int, then I have to explicitly write unsigned int. Okay? If I know I'm dealing only with positive numbers. All right? Similarly, say again, if you are dealing with ages of people, now should I use signed char or unsigned char? Unsigned char. I know ages can't be negative. They can't be negative ages, right? So unsigned char I need to use. Although even if I use signed char, it will not be much of a problem because it will go up to what is the maximum number in signed char? Maximum decimal number which a signed char can represent? 255 or 127? 127. It's a signed char. So half will go for negative numbers. So half will be for positive numbers. So the maximum positive number you can represent using a signed char is 127. So if you know, I mean, 99.9% of the times we know age cannot cross 127, but there can be exceptions where people may exist beyond 127. In that case, signed char will not be sufficient. You have to use unsigned char. Now in signed char, in unsigned char, we know positive numbers, they also map to characters. So we can use those numbers as numbers or as characters. But in signed char, what will negative numbers represent? They represent nothing. Negative numbers just stay as numbers. They don't represent any characters. Whatever positive numbers are there in signed char, they anyway represent their characters. Okay? So if you are dealing with characters, and even if you are dealing with characters, almost all the useful characters will come within 127. It is only in the extended ASCII that you will go up to 255. In normal ASCII, everything will fall within 0 to 127. So most of the times char is sufficient for all practical purposes. Although the range you are using is 0 to 127, you are not making use of minus 127 to 0 range. Usually we don't use. Okay, so that is how you understand the difference between signed and unsigned numbers. And char, if you know your integers are falling between 0 to 255 or minus 127 to 127, if you are dealing only with these numbers, then you use a char data type. Or if you are dealing directly with characters, use a char data type because they will all fall within 127. That's it. Otherwise, use int or shortened or long int, whatever. Okay? Fine. Now, at the end, I left you with a question. What about 0? we looked at positive numbers, negative numbers, but what about 0? 0 will also have two representations, plus 0 and minus 0. Now, technically both are same, plus 0, minus 0, there is no difference. So why wasting space? One for plus 0 and another for minus 0. Okay, can we optimize it further by using only one representation for 0? And one of these two representations, either plus 0 ka or minus 0 ka, use it for some other number. So we are trying to squeeze every ounce of memory we have and trying to make use of it. Okay, that is one thing. The second thing is to removing ambiguity. Two representations for 0, ambiguous. I want only one representation. Okay, that is the second thing. So for that, the solution is something called R's complement. So what do we mean by R's complement? So I will tell you, R is base of the number system, whichever number system you are dealing with. So R's complement is not specific only to binary system. It is applicable to any number system. Okay. So this R is basically also called radix. That is why it's called R's complement. And capital N is the number whose complement we want to find. And small n is number of digits in capital N. Okay. And the formula for R's complement is R's complement of n in base R is R power small n minus capital N. Okay. So let's look at some examples. You will get a clarity. Suppose I have 7 in base 10. So what do we mean by complement? The idea is, if I want to do A minus B, one way is to actually perform the subtraction operations. All right, but these subtraction operations also involve a lot of borrowing operations, right? If the digits in the first number are smaller than the digits in the second number, then we need to borrow from the left side, left digit to the right digit, and so on. So many borrowings we need to do, and also so many subtractions we need to do. So you are performing too many operations. You see, when you are building a machine, when you are discussing theoretically, anything is fine. But when you actually sit on to build a machine, you need to think of not only the output, but also how efficiently you can reach that output, right? So it's like simple. If I want to go from point A to point B, I can either go in a straight line, or I can go all around the world and then come to point B. I can do it in any way. But given a choice to do it efficiently, we just choose a straight line, right? So same thing when you code, when you are asked to solve a problem also, this is something which you need to keep in mind, even in interviews or whatever. If you are given a problem, they just don't look at whether you are reaching the solution or not. They also look at how you are reaching the solution, how efficiently you are reaching the solution. Okay, so they can ask you, okay, the solution is correct, but can you optimize it further? Can you optimize it further? Can you reduce the complexity? Can you do it faster? All these kind of questions they ask. Similarly, when we are performing operations like addition, subtraction, whatever they are, can we optimize it further? That is the question. Okay, so to optimize it further, rather than performing actual subtraction, what we do is, when we say A minus B, we convert it as A plus of minus B. Okay, this minus B can be acquired by calculating something called B's complement. So we will see. So now when you have B's complement, you add this B's complement to A, that is equivalent to doing A minus B. So rather than subtracting, you are adding two things, which means finding B's complement should be more optimal than performing actual subtraction between A and B. Only then this is useful, right? Otherwise, you better do just the subtraction A minus B, right? Okay. So we will see. So if 7 is in base 10, 7's complement. So first of all, what is R here? 10. What is capital N? 7. Small n? 1. Okay. So now 10's complement of 7 in base 10 is 10 power 1 minus 7. That is 3. Okay. Now let's take another example. I will show you why we are doing this. So let's take say 247 base 10. Now again, R is 10, capital N is 247, small n is 3 digits. All right. So now 10's complement of 247 base 10 is 10 power 3, 10 cube minus 247. So this is 1000 minus 247. Now you see so many borrowings I need to do. Okay. So first I borrow 1 from here. This will become 10. All right. So this will become 10. Now, so this will become 10. And then again I borrow 1 from here to here. This will become 9. This will become 10. Now I borrow 1 from this 10. This will become 9. This will become 10. So 10 minus 7, 3. 9 minus 4, 5. 9 minus 2, 7. This is anyway 0. Okay. So now you see, you need to do 3 borrowings and 3 subtractions. All right. Imagine you have a million bit number, or let's say 100-bit number. You need to do 100 borrowings and 100 subtractions. So let's do it for binary also, and then I will tell you the solution. So for binary, okay, let's not worry about binary. So let's directly look at the solution, and then we will use the solution for binary numbers. So the solution is this same 1000 minus 247. I can also write it as 999 plus 1 minus 247. Right? Now I need not borrow anything because 9 is the largest number in that base 10 system. So any other digit will be either equal to that or less than that. So you don't need to borrow ever if your first number is all made up of 9s. Okay. So now half the operations are reduced. Earlier you were supposed to do 100 borrowings, 100 subtractions. Now you only need to do 100 subtractions. 100 borrowings are gone. Okay. So that is like reducing the effort by half. That's a great optimization. So 9 minus 7, 2, 9 minus 4, 5, 9 minus 2, 7, plus 1, you get the same result. Right? 753. So this is a simpler method. So rather than finding the complement by subtracting it from 10 power n, whatever is the base number, that base power number of digits, you find the complement of 10 power n minus 1. Okay. So that you will get the largest number with those many digits as your first number, from which you can subtract the other number, and then you add the remaining one. So you're doing say 100 subtractions. Now only one additional operation you're doing is adding plus 1. That's all. Okay. So now what we are interested in is, suppose I want to do a minus b. This is equivalent to saying a plus of minus b. Okay. Now minus b is equivalent to r's complement of b. This is also equivalent to r minus 1's complement of b plus 1. Okay. So when I took 7, 10's complement of 7 is 3. That same 3 I can achieve in two ways. One is subtract 7 from 10 directly, or subtract 7 from 9 and then add 1. Okay. So when I subtract 7 from 9, what do I get? 2. This 2 is called 9's complement. 3 is called 10's complement of 7. 2 is called 9's complement of 7. Similarly, in this case, 753 is called 10's complement of 247. 752 is called 9's complement of 247. So r minus 1 complement. So to find r's complement, there are two ways. Subtract n, capital N, directly from r power n, or find r minus 1's complement and then add 1 to it. Okay. So the second method is faster and more optimal. So now imagine, let's do it for binary numbers. Suppose this is in binary. So here what is r? R is what? Base. That is 2. Capital N is 1101. Small n is 4. So now 2's complement of 1101 base 2 is 2 power 4 minus 1101 base 2. 2 power 4 is 16. 16 in base 10 minus 1101 base 2. 16 in base 10 is what in binary? 16 in binary is what? Huh? 1000. 1 and then 4 zeros. Simple. 10 cube means 1 followed by how many zeros? 10 power 5 means 1 followed by 10 power 100 means 1 followed by 2 cube means 1 followed by 3 zeros. 2 power 5 means 1 followed by 5 zeros. 2 power 100 means 1 followed by 100 zeros. So 2 power 4 means 1 followed by 4 zeros. That's it. Same thing is applicable in this system also. Okay. So 1 followed by 4 zeros minus 1101. Okay. This is what we want to do. So let me move this to the next page. So now let me bring it here. Minus 1101. Okay. Now I need to do again 4 borrowings. All right. So this one I borrow here. What will it become? Huh? 10. 1. Where is 10 coming from? This is binary, Baba.
2.
It is 2. You see, now you understand that you never learned subtraction. Whatever you learned in school, you did it mechanically without understanding what is happening. When you borrow one unit value from a higher place to the next position, its value is increasing 10 times. Now, in a binary system, when you borrow 1 unit, when it's coming to a lower position, its value is increasing 2 times. So the 1 in the higher position becomes 2 in the lower position. From this 2, if you borrow 1, this will become 1 and the next one will become 2. Okay. So this one you take 1 here, it comes here, it becomes 2. This 2, you again lend 1 from this 2 here. This will become 1, this will become 2. Okay? Again, this 2, you lend 1 here, this will become 1, this will become 2. This 2, you again lend 1 here, this will become 1, this will become 2. Okay? Now in the last position, you have 2. 2 minus 1, 1. Now you have 1 here in the previous position. 1 minus 0, 1. 1 minus 1, 0. 1 minus 1, 0. This anyway became 0. This 1, you lent 1 here, this 1 became 0. So this is anyway 0. So you are left with 3. You can cross check. This is 16. This is, what is 1101 in decimal? I'm getting so many different answers. 26, 13, 5. Quite simple. It's 13. And this is 3. It's matching. That's it. Right? Okay. So today you learned something new. How to subtract two numbers. Which you thought you learned, which you thought you knew. You were under an illusion for 17 years of your life. Okay. So subtraction happens like this. When you borrow 1 unit from the higher number, in the next place, it becomes that base so many times. Okay. If the base is 10, it becomes 10 times. If the base is 2, it becomes 2 times. If the base is 8, it becomes 8 times. All right. Okay. So now this is a complex way of doing it. So a simpler way of doing it is, what is the simpler way of doing it? To find r's complement, two ways we thought. One is r power n minus n. Second way is r minus 1's complement plus 1. Okay. So r minus 1's complement, of b plus 1 is nothing but, r minus 1's complement is nothing but r power n minus 1 minus n or minus b. Why? R power n is, if it is decimal, r 10 power 4 is 1 followed by 4 zeros. Okay. But I want not 1 followed by 4 zeros, but I want only 4 nines. Okay. So what is that? 10 power 4 minus 1. So that will give me 4 nines. So from that 4 nines, I subtract b. And then finally I add 1 to it. I get 10's complement. Similarly, if I want to find 1's complement, it is 2 power n minus 1 minus b. Finally plus 1. Okay. So 1's complement of this 1101 base 2 plus 1. Now 1's complement of 1101 base 2 is 2 power n minus 1 minus this n 1101 base 2 plus 1 is, total thing is 2's complement, but up to here it is 1's complement. Okay. So if you do that, it is 4 1's minus 1101, right? Like there were 4 9's there. I have 4 1's here. 1 is the largest digit in binary. Anything has to be equal to or less than that. Fine. So the answer is 1 minus 1 is 0. This is 1. This is 0. This is 0. Okay. So this was, what is the value? 4 1's means what in decimal? 15. This is 13. This is 2. Finally, you should add 1 to it. You will get 3. That is 2's complement. Okay? So you add 1 to 1's complement, you will get 2's complement. Fine. Now these are all various ways of. So let me put it here. I add 1 here. I get 0, 0, 1, 1. Okay? So this is 1's complement. This is 2's complement. Okay? Fine. So now the point is I add 2's complement of a number to subtract it from another number. Okay, so rather than subtracting b, I find b's complement and add it to a. This is a much easier operation now. Even 1's complement, it is a much easier thing. Actually, you did not even perform subtraction as such. Do you notice a pattern there? Do you notice a relation between 1101 and 0010? Huh?
Like if it is 1, the output is 0.
Right. They are inverse of each other. 1101 inverse is 0010. Each bit is inverse. So this is like NOT operation. So these bits you send to a NOT gate, you get 1's complement. Then you add 1 to the output, you get 2's complement. That's it. So you need not perform complex operations like borrowing, this, that. Input, NOT gates, output plus 1. That's it. You get the complement of the input. Fine. Now this output you add to the original number, you get the output. Fine. So now let's quickly see. Okay, this is all done. How many bits we need to represent a character? Standard communication, we know around 255 characters are considered standard. How many bits do you need to represent number from 1 to 255? It's a bad question. The better question is, what is the least number of bits we need to represent numbers from 1 to 255? Because imagine I want to represent number 256. Right? Now, how many bits do I need? Number 256. It won't. Number 256 cannot be represented using 8 bits. Okay, you can say 16, but the point is, what is the least number of bits that you need to represent 256? 9, right? So you can represent beyond 256 also, but minimally you need 9 bits to represent 256. All right. So that's the better question. So answer is floor of log n base 2 plus 1. So whatever number you take, suppose you want to represent 300 in bits. So for 300, minimally you need 9 bits. Okay. So 300 base 2 will be something like 8 point something plus 1. It will be 9 point something. You take the floor, you will need 9 bits to represent 300 plus something. Okay. Fine. So whatever n is there, you take log n base 2 plus 1. That number will be a real number, but number of bits is always an integer. So you take floor of the real number. Whatever is the answer, that is your number of bits. Fine. Unsigned char is a positive integer that only takes 8 bits. We just discussed it. Unsigned char is only positive integer and its size is 8 bits. Basically, it's an integer data type with size 1 byte. Char is a signed integer that only takes 8 bits. Any data type, if there is no prefix, signed or unsigned, the default thing is signed. Okay? If you want it to be unsigned, you have to explicitly mention unsigned. Now, negative numbers using 8 bits. How do I represent signed integers? Reserve 1 bit exclusively for sign and use the rest for magnitude. What about ambiguous zeros? Plus 0, minus 0, you have 2 representations. What about that? You need to use 2's complement method. What the hell is that? Okay. Now, these are various representations for binary numbers. Okay. If you notice, just the top half, above zeros. In all the 3 systems, the representations are same. Okay. Positive numbers are represented exactly identically in all the 3 systems, whether it is in signed magnitude system or 1's complement system or 2's complement system, they have the same representation. The difference comes when you come to negative numbers. Okay, if you take the simpler thing which we thought in the beginning, whatever is the positive number, the first bit is only sign bit, the remaining is only magnitude. Okay, so whatever is plus 6 representation, same you will have in minus 6. The only difference is first bit is 1 instead of 0. Like you see plus 3 minus 3, plus 2 minus 2. They are same except for the first bit. Okay, this is one way of representing negative numbers. Another way of representing negative numbers is 1's complement. You take the positive number, just invert those bits. You will get complement. You will get 1's complement. Fine. The third method is 2's complement. After you invert the bits, add 1 to them. You will get 2's complement. Okay? So you should never stop with 1's complement of a number. Okay? You have to add 1 to it. 1's complement is an intermediate step. But within 1's complement, this number is represented like this. You need to come to 2's complement to perform the actual subtraction. Fine. Now, what we can do, suppose I want to do 3 minus 2. What do? I take plus 3, I take minus 2, I add both of them. Whatever is the result, that if there is an additional carryover, if I am dealing with 8 bits, I will get a 9 bit as a carryover. I ignored that. Okay? I take only 8 bits. That will be my answer. Now, in these 8 bits, if the first one is 0, that is anyway your answer. If the first one is 1, which means it is a negative number. Okay? Now, this negative number, you can't understand just by separating this one sign bit and the remaining magnitude. It will not be translated like that. That can be done for sign bit numbers. But for 2's complement, 1's complement, etc., if you get this kind of answer, to find what this number represents, you need to convert it. You need to find its 2's complement. You will get some positive number. From that, you understand that this is the negative number of that positive number. Suppose I don't know what this number is. Okay? I find its 2's complement. I find that to be plus 2. So I understand this is minus 2. Okay? So you don't directly understand what a negative number is just by looking at it. You can also, in one way, there is a simple formula for that also. So suppose there's a second method. If I want to find what this number means, then what you do is the polynomial representation I said, you remember? 2 power 0, 2 power 1, 2 square, 2 cube, and so on. Only when it comes to the last bit, it will become 2 power minus 7. Not 2 power 7. Now you add them as they are, 2 power minus 7 plus 2 power 6, 2 power 5, 2. All those, you will get the result. You will get minus 2. That is another way. Okay. Anyway, we need not worry about complete detailed in-depth understanding of these things. The idea is you need to understand that negative numbers now, the benefit is there is only one representation for 0. So you take zeros, you try to find minus 0. How do you find? First you take 1's complement, you will get all 1's. You add 1 to it, what will you get? 1 followed by these many zeros. So there is an additional 1 as a 9th bit. You just ignore that. You will get back all 8 zeros only. So plus 0 and minus 0 have the same representation in 2's complement. So you have saved space there. Alright. Now this particular representation, it has this particular value, minus 128. You can calculate and see. Okay. You can do this, I said no, 2 power 0, 2 power 1 and so on. This will be 2 power minus 7. 2 power minus 7 is what? Minus of 2 power, sorry, I made a mistake. It's not 2 power minus 7. It is minus of 2 power 7. Minus of 2 power 7 is minus 128. So minus 2 power 7 plus remaining powers, 2 power 6, 2 power 5 and so on, you will get the result. Okay? So you got an additional space and it became unambiguous, and you can directly use these numbers to add to get the subtracted, to do the subtraction. Okay? I already shared some videos on Discord related to this. Go through them. They are all 5 minutes, 10 minutes videos. You will understand better. Fine. So this is just for you to understand how a computer stores numbers in binary. Because later we will do bit operations. You will understand. You need to have this understanding to understand how bit operations will happen. Okay.
Hmm.